In this video, I want to introduce stage 3 of your temperature alarm design project. In this stage, you will add a comparator circuit and an alarm output driven by 3 different op-amps. So here is an overview of the circuit, and over here what we're going to have are 2 voltage comparators. Notice that these are op-amps that do not have negative feedback, and so we will talk about what that means in just a moment. The output from these 2 stages then go into a summing amplifier configuration, as we see here, and we're going to sum together those voltages. And finally, the output stage has 2 LEDs, one of which will be green and the other will be red, and those will be used to indicate whether the temperature is within the allowable temperature boundary limits or is outside of that. So, to begin, let's talk about the comparator circuit. So a comparator is an op-amp configuration that runs open loop. Most all of the op-amp circuits that we have talked about thus far have been closed loop with negative feedback coming back in. And that's always the question that we ask ourselves when we're analyzing amplifier circuits like this is, do we have negative feedback? In this case, do we have anything from the output fed back into the input? And as it turns out, in these 2 op-amps, we do not. And so what that means is that any difference that you have between the input at the non-inverting input and the input you have at the inverting input will be multiplied by a very large gain, effectively close to infinity. Theoretically, for an ideal op-amp, it would be infinity. And what that means is if the voltage here at the non-inverting input is greater than the voltage down here at the inverting input, that difference would be positive, and once you multiply a positive voltage by effectively infinity, it would end up saturating at the positive voltage rail. Otherwise, if the voltage down here at the inverting input is greater than the voltage at the non-inverting input, that difference in voltage would be negative, and when you multiply negative voltage by infinity, it effectively saturates down here at the negative voltage rail. So when you don't have feedback, what you're guaranteed is your output will either be a saturation at the positive voltage rail or a saturation at the negative voltage rail. And the reason this is considered a comparator circuit is effectively whichever saturation you have tells you whether the voltage here or the voltage down here is bigger. So in this case, what we're going to do is compare our output voltage coming off of the Wheatstone bridge circuit that you previously designed. So that will be VO right here. We're going to be comparing that to 2 threshold limits. We're going to have V upper, which is going to be the expected voltage when the temperature of the temperature probe is at 50 degrees Celsius. And so that is going to be our upper temperature boundary. And then V lower is going to be the voltage that we expect when the temperature is at 20 degrees Celsius. And so our allowable range is any temperature between 20 and 50 degrees Celsius. So what we want to do with this top comparator is we want to check to see, is the output voltage, is the temperature in fact greater than or less than 50 degrees Celsius. So we're going to run in our output signal from the Wheatstone bridge into the non-inverting input of this amplifier circuit. And over here, what we're going to do is create a little voltage divider. And so that voltage divider will allow us to take 5 volts, and you can choose R5 and R6, such that V upper is as close as you can get it to the theoretical output voltage that you would experience at 50 degrees Celsius. So you can go back to your MATLAB simulation that you've designed and look at your plot, look at the arrays that come out, and figure out what is the expected output voltage at 50 degrees Celsius. And then you'll just choose R5 and R6 proportionally to get this voltage divider to work so that the output voltage here is what you expect the output voltage to be from VO at 50 degrees Celsius. Now, if the output voltage here is greater than that voltage, what that means is the temperature is more than 50 degrees Celsius. And when that happens, your voltage here at IN plus is going to be more than your voltage down here at IN minus. And what that means is you will saturate at the positive voltage rail. So if you see a saturation at the positive voltage rail on the upper comparator, that means the temperature is more than 50 degrees. Likewise, you're going to create a V lower using another two resistors in a pair, and that will establish the voltage that you expect at 20 degrees Celsius. Certainly that will be less than what you expect at 50 degrees Celsius, and you can find that in your plot. And so here we are running that voltage to the non-inverting input on the op amp, and then down here we are also running our output from the wheatstone bridge into the inverting input here. So now if V out happens to be less than the V lower, then this will saturate at the positive rail. So then that would mean that this is greater than this. If this happens to be more than V lower, meaning it's above 20 degrees Celsius, it's not too cold, then it would saturate at the negative rail. So let's think about our possible scenarios that could exist. You can really just have three conditions. You could have a temperature that is outside the range and above 50 degrees Celsius. You could have a temperature that is inside the range between 20 and 50 degrees Celsius. And then you could have a temperature that is below 20 degrees Celsius. Obviously, if you're below 20 degrees Celsius, you also must be below 50 degrees Celsius. Obviously, if you're above 50 degrees Celsius, you also must be above 20 degrees Celsius. So you can see what those comparators would do. So let's do an example. If we are above 50 degrees Celsius, that means VO is going to be greater than V upper. This will saturate at the positive rail. And then we go down, VO will of course also be above V lower. But what that means is down here we're going to saturate at the negative rail. So we'll see a negative output voltage here and a positive output voltage there. If you're in between 20 and 50 degrees, that means that VO would be greater than the voltage you expect at 50 degrees, or sorry, less than, because it's in between. So if you are between 20 and 50, this is going to be less than the V upper value. That means we will saturate this at the negative voltage rail. And then down here, your voltage is going to be greater than the voltage of V lower, so that will also saturate at the negative voltage rail. So in that case, you will see negative and negative. And finally, what would happen if you were below 20 degrees Celsius? Well, if your temperature was below 20 degrees Celsius, then VO would be less than V upper. So that would mean this would still saturate at the negative voltage rail. And now the VO would also be lower than the V lower, and what that means is this would saturate at the positive voltage rail. So those are the three possible combinations that you could see from your comparator circuit. So now that we have these two outputs from the comparator, we're going to run those into a summing amplifier. So here you see the summing amplifier, and if you look at the directions, you're going to have to choose R9, R10, and R11 such that your sum either goes to 0 or goes to positive 12 volts, and you'll have to figure out the math accordingly. And that is so that the output here from VSUM can be used to drive the indicator lights. So in this case we have two LEDs. LEDs are short for light emitting diodes, and a diode is a special electronic component that ideally behaves either like a short or an open circuit. And what I mean by that is if you have a positive voltage here relative to the voltage here, in this case we have 5 volts, so if you had the 12 volt output up here, then this voltage would be greater than that voltage down there. And what that would do is have two different conditions on the LED. Because this voltage is greater than that voltage down there, this would be greater than that, meaning current would flow through LED 2 and it would light up. The arrow on the diode symbol indicates the direction current wants to flow. So if you have positive voltage behind the arrow relative to lower voltage on this end, in this case 12 volts relative to 5 volts, the current would flow this way. That would be a forward bias diode, and it would behave like a switch. In this case, you would have a higher voltage here than there. The current wants to flow this way, but because this voltage is greater than that, and we know current flows from high potential to low potential, this diode would be what is considered reversed biased, and what that would mean is it would be behaving like an open circuit, and no current would flow, and this light would be turned off. So depending upon whether you have 12 volts here or 0 volts here, which are the two options coming out of the summer, if you have a 0 volt here, then this would be a positive 5 volts relative to ground, and now your current would flow this way, and that would turn on LED 1. So what you are going to expect to see from this circuit is that one or the other LED, but never both, will be on at any given time. If you're going to wire it up so that you have a green LED and a red LED, and if the temperature is between 20 and 50 degrees Celsius, you want the green LED to be on, and if it is outside of that range, if it's too hot or too cold, you want the red LED to be turned on. And so the purpose of this part is going to be to design and choose the resistor values. In this case, you're going to choose R12 so that it limits the current through LED 1 and LED 2, and you'll see the current limitations in the assignment. So you'll just pick that to be sufficiently large that it limits the current. In the previous stage, you're going to pick R11, R9, and R10 so that you get the proper multiplier of your different voltages coming in off of the two comparators. And then in the comparator circuit, you're going to pick R5, R6, R7, and R8 so that you're establishing the V upper and the V lower, just making voltage dividers. So that will be all you'll be doing in stage 3. I will also post a document with the expectations of what will need to be in your report. You will write one report for every lab team, and so you can pool your data with your lab partner and just write one report together. But just make sure in the lab that you test out everything in your circuit. So what you should do is look at your wheatstone bridge, make sure your voltage outputs are changing as appropriate with respect to the temperature, and then you can check to see when these comparators switch. So you can use the multimeters on your bench to check to see when at what temperature things switch. In the lab we have thermometers, so you can put thermometers inside of water baths that you can start as either hot or cold, and as the cold water warms up to room temperature, you should see a switch from the extreme cold end back into the allowable end, and then you can also heat some water on a hot plate, and that will allow you to start at start the temperature probe at the extreme hot end and allow that to cool down to room temperature. That's how you're going to gather some data that you're going to need for the graphs. So we will work on that this week and next week in the lab. So with that, these are your stages you're going to be designing and picking resistor values. Make sure your wheatstone bridge is working appropriately, so collect some data along the curve to make sure it is following what your simulation said, and then ultimately you'll put everything together and you should see the light switch. And one of the things you're going to be asked for in your report is at what temperature did the light switch. So it should be very close to 20 degrees and 50 degrees Celsius. If you're way off by that, you might want to go back and recheck your resistor values. Good luck.